let's start there. Okay, let's get started, guys. There's a handout today. Please pass it around all the way back. We'll do half and half. If you don't get one while it's coming around, you can get one near the end. There's other postings on YouTube. I am going to do the nomenclature only on video. I'll put that up today. We'll talk more about it. Also, the IR is there. I also sent handouts to you by email. And we will get into one of those today, the physical properties handout. Okay, let's look at hybridization. We went over most of the stuff. I'm not going to sort of go back to where we were, but let's move ahead with predicting hybridization. We also need to stay with the green sheet because we need to look at some the bond lengths, etc. is going to be in our functional groups handout on the very back. I reckon we'll go ahead and do this. We'll go kind of back and forth. This hybridization is carved right here in Cipro. Okay, it's SP2. How do you know it's SP2? 3 regions. Yeah, 3 regions. You see a double bond, it all kind of leads you to SP2. Okay, if this carbon is SP2, what is that going to look like? Can you graph it? Okay, we graph this. If an SP2 has how many hybrids? 3 hybrids. They're called SP2s. There's 3 SP2 hybrids. What's left over on that carbon?
1 p orbital.
A p orbital. Okay, what type of bonds do you see this carbon making? I see a sigma bond to carbon, and sigma bond to oxygen. We use hybrids to make sigma bonds, sigma bond to carbon, sigma bond to carbon, sigma bond to oxygen. What other type of bond do you see that carbon making? Pi bond to oxygen. 4 arrows are the 4 valence electrons of carbon that it brought to the dance. The other electrons came from the other atoms. You now have an octet. What is this here? That's a double bond to oxygen. Sigma bond, pi bond. Okay? Your hybrids set your geometry. How are these 3 spread out?
Planar.
Trigonoplanar. The carbon's trigonoplanar. It is the 3 regions are trigonoplanar. That is, this bond angle, here is what?
120 degrees.
120. It's 120 all the way around there. 3 bond angles. And that's basically it. So we graphed it here. This is this energy, very simple. I'm probably the only one I know that does graphing of hybridization beyond the introductory 30 minutes. I think this is very powerful. I ask you to do it, and we'll do more of this. And when we get to organic 2 and I say graph hybridization, well, that's it. Question?
When we graph the hybridizations, do you want us to draw the 1s orbital as well?
No, not necessary. That's just dealing with the valence. Okay. Well, since we're already here, we need to go over to the bond lengths, bond strengths. What about the oxygen? What's its hybridization? What's missing on the oxygen? 2 lone pairs. 2 bonds, 2 lone pairs, standard for oxygen. Okay, how many electron regions around the oxygen? 3. Double bond region, lone pair region, lone pair region. 3 regions is going to require what type of hybridization? Okay, it's sp2. That means it's got 3 hybrids and a p. What type of bonds do you see the oxygen making? Sigma bond to carbon. And what else do you see that? What other type of bond? Pi bond to carbon. And this here is what? That's your double bond to oxygen. To carbon. We're talking about oxygen. Okay? So where are the lone pairs? They're there. They're in hybrids. Okay? That's it. And if you drew that oxygen, and you drew the hybrids around the oxygen, you would draw 3 hybrids. How would they be oriented? For what geometry? Trigonoplanar. one here, one there, one there. I don't have enough room to bond to carbon now. But there's lone pairs here. And then there's only one electron here. This is making a bond, so we need an electron from carbon to make that sigma bond down there. But lone pairs are just these hybrids, and that's trigonal planar. And then there's a p orbital left over. It's coming out, but that carbon also has a p orbital, and that's how you make the pi bond. There, it's sp2. Okay. Let's do the nitrogen, the middle nitrogen there of ambient. What's missing?
Lone pair.
Lone pair, 3 bonds. What's the hybridization of that nitrogen? Sorry. I didn't want to do that one. I want to do this one up here. Lone pair. What's the hybridization of that nitrogen? It's sp2. Why? It's got 3 regions around it. Double bond region, single bond region, lone pair region. 3 regions is sp2. Now that we get that far, we draw sp2, 3 hybrids and a p orbital. What type of bonds do you see that nitrogen making? Single bond to carbon. Single bonds are sigma bonds. Use it to hybrids. Okay, sigma bond to carbon. Sigma bond to carbon over here. What else do you see it making? Pi bond to carbon. That's using the p orbital. All together now, what is that? Double bond to carbon, single bond to carbon. Okay, by default, where's the lone pair? That's right there. So the answer to the question is the lone pair is in what type of orbital? Lone pair is an sp2 hybrid orbital. That's where it's got to be, because the other orbitals are being used to make the other bond. All right, I'm dying to get to the other sheet, but let's stay here. So what about the other nitrogen of, the middle nitrogen of ambient? Let's have a lone pair, because nitrogen makes 3 bonds, 1 lone pair. Question?
I have a question about the last nitrogen. Aren't all the electrons in sp2? Well, like all the valence electrons?
No, one of the valence electrons is a p orbital. That's the second bond of the double bond is a pi bond. And it's made using p orbitals, not hybrids. Second bond, double bond is the, we drew that last time with carbons. Nitrogen is no different, it just has one less, it's not like these atoms have ends on their back or anything. I mean, ultimately they're all just electrons and protons. It's the same thing. Was there another question?
So pi bonds are always going to be in the p orbital?
Pi bonds are made using p orbitals. Pi bond is a side-to-side overlap of p orbital. Sigma bond is head-to-head, and usually that's, I say usually, but I think pretty much always, hybrids make head-to-head sigma bonds. P orbitals make side-to-side pi bond. And your second bond there is a pi bond. So what about the middle nitrogen? Somebody said sp2. How many regions around this nitrogen? I see 4. I see 3 single bonds and a lone pair. It looks like 4. This is an exception. Okay? This is an exception. It's actually sp2. sp2. But now that I've told you it's sp2, now graph it. Well, okay, he said it's sp2, so that means it's got to have how many hybrids? 3 and a p orbital left over. That's sp2. What type of bonds do you see that nitrogen making? I see 3 sigma bonds to carbon. Sigma bond to carbon, sigma bond to carbon, sigma bond to carbon. By default, where's the lone pair? Lone pair in p orbital. Both of these are sp2, but the lone pairs are very different. That one's in a hybrid. This one's in a p orbital. Why is it in a p orbital and why is it an exception? Here's sort of the take-home. It's written in my notes and stuff. Anytime a lone pair is next to a p orbital, the lone pair is going to want to be in a p orbital too. Okay? Does a neighboring atom have a p orbital? Does that carbon have a p orbital? Yes. Yeah, if we graph hybridization, it's sp2 with a p orbital. P orbital, p orbital. This p orbital is all next door. Okay? All right, let's try some demo here. Okay? Well, we've got a 1, 2, 3, 4, 5. We've got a 6 atom link here. Okay? Y'all have p orbitals. You three, hold your hand up. P orbital, okay? P orbital. P orbital. That's the p orbital up and down, okay? All right. You're going to have a lone pair. You just said 5. You have p orbitals. So hold it up. Okay. So let's focus on you. You have a lone pair. All right. Now, if we call you sp3 like y'all wanted to do before we started, would an sp3 have a p orbital? sp3 don't have a p orbital. So, see, it's like all these p orbitals here, you want to kind of play with them because if you have a p orbital and you line up with them, that's called conjugation. P orbitals lining up is orbital overlap. So you three are overlapping. You two are overlapping. But we got a break in the line here. This molecule would like to have continuous p orbital overlap if possible. That's a good thing. That'd be extra bonding. Now, if we make you sp3, you're going to be tetrahedral, and your two things are not going to go straight up, but you're going to go like this. So hold your lone pair towards me. Okay, pretend that's a lone pair. You're still not interacting with them. You've got to be straight up and down. All p orbitals have to be straight up and down to interact. So, but you really want to do this because it'll make you lower in energy. So what happens is, instead of you being tetrahedral, you adopt the trigonal planar and move your lone pair straight up. And once that happens, we have this magic of now we have 6 p orbitals all lined up. This is a better thing. But it requires this atom to be sp2 with a p orbital. Now what's going to be in the p orbital? The lone pair. The other things aren't going to be in p orbitals. So the lone pair moves in a p orbital, it all lines up, and now you have, if we drew these p orbitals, there's p orbitals all the way around. There's p orbital there, p orbital there, that's overlapping to make pi bond. It's hard to do here because p orbitals here. It's all overlapping. It's all overlapping. All we need is one, really. That's got a p orbital. We already did that nitrogen, right? I mean, yeah. See, this guy feels left out. If we say sp3, there's no p orbital. Instead, we're going to say, okay, we're going to make you sp2 and give you a p orbital too. Now you can interact with all the others. Getting sloppy there, but p orbital interaction is good. It's orbital overlap. But the lone pair moves into the p orbital, and then this is how it exists. Lone pair in p orbital. The 3 hybrids are used to make the 3 bonds, you see. That's an exception. It leads to extended p orbital overlap, which we call conjugation. Ultimately, we'll call it resonance. Conjugation is a good thing. When does this happen? Anytime you see a lone pair next to a p orbital, the lone pair is going to want to be in a p orbital if it can. Typically can. There'll be some exceptions to the exception. Question?
Is that also with like an oxygen too?
Even
Or is it
any
just
atom.
with
Any
oh,
atom. Any atom. Okay. What's hybridization of this nitrogen? It's the same thing. It's sp2. sp2. The lone pair is in what type of orbital? P's in p orbital. Why? Because over here you've got pi bonds. But see, this nitrogen is like, would love to interact with those p orbitals. But if it's sp3, it doesn't have one. So we're going to say it's sp2, and this becomes solvent. Lone pair here, one electron, one electron. You get a 3 p orbital system. You just have to know that that's taking place. There's only some extra bonding going on there that we don't really see if we look at just a static structure. Now the big difference, lone pair that's in a p orbital is not going to be basic because it's busy doing conjugation stuff. That nitrogen is not basic. That nitrogen is not basic. Here the lone pair was in a hybrid. It's basic. Okay. Let's do another one. What we can do right here. What's the hybridization of this oxygen here? There's 2 lone pairs. Graph the hybridization of that oxygen. What is the hybridization? sp2, yes. So it has 3 hybrids and a p. What type of bonds do you see it making? Sigma bond to carbon, sigma bond to H. What else is on the oxygen? 2 lone pairs. One of them is in a hybrid, the other is in a p. So if you drew the orbitals of that oxygen, there's trigonal planar. That's supposed to be the 3 hybrids. Okay? I could draw them like orbitals if you want. Okay, but pretend those are the hybrid orbitals. This one's interacting with an H. This one's interacting with a carbon. What is coming out here in this orbital? Lone pair. Okay? Tell me if you can't see. I'm getting a little low here. This carbon is bonded to an oxygen, isn't it? Isn't it double bonded to that oxygen? Yes. So we got a pi bond here. 1 electron each. Interact to make pi bond. So you got the 2 p orbitals. This oxygen wanted a p orbital too. That's why we made it sp2. That's why nature made it sp2. Now, really, these p orbitals are all coming out of the board. If I draw a p orbital on that one, what's in that p orbital? Lone pair. But see, it's interacting. Just because it has a lone pair doesn't mean it can't interact. So one of these lone pairs is in the trigonal planar hybrid system. The other lone pair is in a p orbital interacting with the other pi system.
So why is this more stable than being like SP and having both the lone pairs interact with
They both can.
Okay, only one can.
Because if it was SP, you want to make both lone pairs p orbitals?
Sure.
Okay. How would those p orbitals be the geometry relative to each other? Let's do it here. I don't know if this works or not. You guys hold your p orbitals up. Just one arm. Straight up. Okay. Now we're going to make her, you've got 2 lone pairs now. Okay. Let's make you SP. So now you're going to have 2 p orbitals. How are your p orbitals going to be oriented to each other? If one is straight up, how's the other one going to be? No. The other's going to be horizontal. Okay? Hold it straight up. Real tall, guys. Real tall. Okay? Tall. See, the other one is going to be horizontal. It's not interacting with those. So they don't have any coming this way. Okay, you got to remember, there's resisting of the p orbitals. Just because they're adjacent don't mean they're interacting. I mean, it's kind of like this. I think that these two are interacting. That one is not interacting with anything. So that's no good. So it's got to be able to interact. Question?
So you said that with the lone pairs in the p orbital that it would be basic to run something like this where you view a lone pair and a hybrid and in the p orbital?
One of the lone pairs is more basic than the other. But with oxygen, oxygen is inherently not that basic anyway. And with a nitrogen, you only got one lone pair. So let's move ahead. I'm sure there's questions. There's questions in the warm-ups and the workbook. You do have that exception. Anytime a lone pair is next to a p orbital, it's going to be in a p orbital, as long as they can overlap.
Could we do like the nitrogen to the bottom for anti-aging one? Or anti-aging, the bottom?
Which one? Verapamil?
Yeah, that one.
Which nitrogen?
The middle nitrogen.
Verapamil at the bottom, middle nitrogen. What's the hybridization? That's sp3. If you graph it, you'll have 4 hybrids, no p orbital. That nitrogen doesn't have p orbital. 4 hybrids, 3 of the hybrids making sigma bonds, and the lone pair is in the 4th hybrid. There's no exception there. Because that lone pair is not next to a p orbital. So it'd rather be in a hybrid. The hybrid is lower energy than a p. But if we can make the p's overlap, that trumps the other thing. Okay. As always, there's plenty of questions here. We need to sort of move on. Some kind of questions for next time, etc. Let's look at the back of the other handout, one that has the drawing. We need to go back to the bond streams, etc. Guess what? Once we move on to acid-base, we'll refer back to hybridization, lone pairs. Once we move on to reactivity, you got to know where lone pairs are at, what type of orbitals they're in. That affects the reactivity very greatly. Let me get this erased. The main thing we're going to look at here is the bond angles are pretty, that's all basically review. For me, everything's about 109.5. It can be compressed down from that. Let's look at the length of the carbon-carbon bonds in each of these compounds. Or more precisely, the interatomic distance. Because this is really a double bond. Interatomic distance between the carbons. These 2 carbons are further apart. Okay? The bond is longer than the double bond. And then the double bond is longer than the triple bond. That's all based on the types of orbitals that are being used to make the bond. And really the hybrids. What type of hybrids are making this bond here? sp3, sp3. That's that bond here. These 2 orbitals are overlapping to make that single bond. The sigma bond here is what? sp2, sp2. And of course here the sigma bond is sp, sp. Now in this particular setup, both are the same. Doesn't have to be. What do we know about these orbital sizes? Which is a longer orbital, sp or sp3? sp3 is a longer orbital because it has more p character. Basically, you talk about s character here. This is what? 25% s? And this is what? 50% s. The more s character, the more rounded and not as long. Rounded like a volleyball. The more P character, the more longer it is, like dumbbell. So it's going to be a longer bond. So that's where your bond links come from, type of orbital that's used. Let's look at the strength of the CC bond. Now you can do kcal or kilojoule. I'd probably go kcal. That's 90, 174. But hold on. They're actually not just talking about the sigma bond. They're talking about the entire bonding. Here we got a double bond. That's obviously stronger than a single. But is it double? No, it's not double. Because a pi is weaker than a sigma. Pi overlap is not as strong because it's side to side. But you also have a difference. The sigma bond here is sp3, sp3, and the sigma bond here is sp2, sp2. That's sort of convoluted there. Let's just focus here. Two sigma bonds. Which one's stronger? This one or this one? This is going to be stronger. Okay? Why? Because the orbitals are more stable. What's the percent S here? Yeah. The more S character, the lower in energy your orbitals. I mean, isn't an S lower than P in energy? Thus, the more S character, the lower. These two orbitals are lower in energy than those two orbitals. The lower energy orbitals make stronger bonds. So that's pretty straightforward. How do you get 174? It's sort of a combination of two different sigma bonds. Just don't worry about it. The main important thing is, do you understand, the more stable your orbital, the stronger the bond it makes. Same thing with the length of the CH bond. As you go down, the H has no hybridization, it's just an S. But this is an SPH, this is an SP2H, and that's an SP3H. The H orbital is no different. The difference is the carbon. Which bond do you expect to be shorter? The one using the SP orbital, because that's a shorter orbital. And hopefully that's what we get, right? Isn't it shorter? Not by much, but the trend holds and you get the right answer. Now, which bond would be stronger? Don't look over there. An sp3as or sp2s or sps? Yes, because the carbon orbital is lower in energy, it's going to make a stronger bond. Okay? All this is based on what type of orbital is being used and understanding the energy of the hybrid and the length of the hybrid. Hopefully it's pretty straightforward. Questions on that? Does that mean it's pretty straightforward or it's not? Question?
I don't know.
Percent S character. Percent S character gives you the answer. More S character, shorter orbital, and more stable orbital. More stable orbital, stronger bond. I mean, you can do one down at the bottom. What did you say down there? Which bond is longer, A, B, or C? Which bond is longer, A, B, or C?
C. Hey.
Because it's made using what two types of orbitals? sp3 orbital overlapping with sp3 orbital. B is made using what type of orbitals? sp3 hybrid interacting with, that's an sp2 hybrid. And then C is sp2, sp2. A is longer than B, and then C is the shortest. So that's the same trend we talked about. Question?
Can we assume that if the bond is connected like a double bond or a triple bond,
I would determine the hybridization and then know what type, I mean, this carbon here is, what's hybridization of this carbon? It's sp2, it has 3 hybrids. I mean, the single bond it's making to that carbon, what type of orbital is this carbon using to make this, the single bond to the other carbon? It's using the sp2. I mean, I'd rather you understand all that, but that's going to become more powerful that way. Be able to answer me questions as opposed to just sort of learning. I'm not sure what you said at the beginning. If you fully understand all that, you'll be able to answer a lot more questions. At this point, we're kind of finishing up hybridization. We're going to move on to physical properties. That handout. Is there anything? I know what we want to do. There's a couple things on the green sheet that we didn't do. Other hybridization examples. We can do that. A word about MO theory, and then we'll move into polarity of covalent bond. Carbocations. Here we go. CH3, and I showed you a plus charge. What's the hybridization of this carbon? Also, go ahead and graph that hybridization. So this is condensed down to just basically formula. What do we got here? Carbon bonded to what? 3 H's. All right, I'm not going to worry about geometry. Anything else on this carbon? Is there a lone pair here? No, there's no lone pair. If there was a lone pair, it wouldn't be a positive charge. There's no lone pair. Why is it positive? Because how many electrons is the carbon owning? 1 of each bond, 3. It's supposed to own 4. It's missing 1, so it's a positive charge. It's a cation. We call it a carbocation because it's a carbon with a cation. What's the hybridization of the carbocation here? How many electron regions around it? What's hybridization? sp2. Now that it's sp2, what do we got? 3 hybrids? And a p? What type of bonds do you see making?
Sigma bond to H.
Sigma bond to H 3 times, right? Okay, that's it. What's in this orbital?
Empty.
Loneliness.
MTP orbital. Do we have to draw that orbital if it's empty? We'll certainly talk about it because when we talk about reactivity, we'll call this electrophilic. What does that mean? Likes electrons. Uh-huh. Why does this like electrons? Because it doesn't have an octet. We'll talk about the electrons sort of filling the MTP orbital. So what's the geometry of this atom? Trigonoplanar. So really, it's boom, boom, boom. The bond angles all the way around of what? There you go. Trigonoplanar, planar on the board, nothing coming out or back. What's left over on that carbon? So you'd have to
Positive charge.
have a deep discussion about what nothing means. But if there's a p orbital there, it's coming perpendicular to that plane, so it's coming out and back. Okay? If I held a dumbbell, half of it would be coming out towards you, and half would be going back, perpendicular to that plane of the sp3. An empty p orbital. There you go. Is what we just did any different from what we did when we had the drug sheet up? Hopefully you see it. No. It's the same discussion, same questions.
If there's nothing in the p orbital physically exists.
That's what I said. You gotta maybe ask Dr. Zuckerman.
Okay.
I couldn't tell you. You also got to remember that all that is fundamentally math. Okay, how about CH3, but let's put a lone pair there. What's the charge of this? It's now minus, because if we drew it out, we'd have 3 bonds to H, lone pair, the carbon's owning 5. It's got one more than 4, so it's minus. That's called a carbanion. That's possible. What's the hybridization of this carbanion? sp3. So it's got 4 sp3s. What else? No, what else? What other types of orbitals does it have?
Age. It's got an age.
No. That one had a p orbital left over. Where did we put it?
We erased it.
You don't look like it was ever there. Is there anything left over here? That's the question.
No.
No, there's no p orbital. I see lots of times students think that sp3 has a p orbital. I'm like, no. Why what?
If it was attached to something that had a pi bond near it, would it have to be a p orbital?
Yeah, if the neighboring atom had a p orbital, this lone pair would want to be in a p orbital.
Okay.
But it doesn't. But by itself, it's sp3. We got sigma bond to H, sigma bond to H, sigma bond to H, and then the lone pair is there. What's the geometry of those hybrids? Tetrahedral. That is, tetrahedral is 2 in the plane, with this being 109.5, 1 forward, and 1 back. 1 forward, we can make a bond here. Let's make this a lone pair. Okay? I mean, this is an orbital. It's a hybrid. They're all orbitals. That's an orbital, that's an orbital, this is an orbital. It's just this one is interacting with an H, right? That's just an orbital with a lone pair. But it's still in that tetrahedral arrangement of those orbitals, right? So that's a carbanion. We've already done the drug examples. Key exception there we already went over. Word about oxygen. Do what? Question in the back? Why is the lone pair doing what? I don't know. What is that? Pauli exclusion principle? Who is that? Wolfgang Pauli? He's about 26 years old when he came up with all that stuff. Okay, oxygen. If you're asked to draw a Lewis structure of oxygen, you might do one like this. Two bonds, 2 lone pairs, 2 bonds, 2 lone pairs. Looks like it's double bonded there. Okay. This looks like a good Lewis structure. Yeah. Fortunately, it's not correct. Thing is, here, and what we're all doing, and we'll do 99% of the time, is we always have electrons paired. It's a lone pair. Pair, lone pair. It's a bonding pair, 2 electrons. Bonding pair. Everything is paired. But oxygen is known to be paramagnetic, has magnetic properties. And those magnetic properties only come from having an unpaired electron. So where's the unpaired electron? Now, that's a 2 electron bonding pair. Okay. Basically, the Lewis structure, valence bonding model, which we're doing and we will continue to do, sort of has some limitations. And in some cases, it's not entirely correct. And this is an example. Okay? To understand why this is paramagnetic, you have to look at MO theory. And that better explains it. And if you do MO theory, you'll see 2 unpaired electrons. Okay? It's a different theory, but the introductory theory is your valence bonding, which we're doing. Right? Organic 2, I cover MO theory when we do aromatics. All right? That's about the last I'll say of MO theory for a long time. There's some advanced chemists where all they do is MO. But for the beginner, we'll stick with the valence bonding. It's a lot easier.
That's great.
Okay. Let's move to polarity. Physical properties. I got these handouts. I asked you to print them out. There's 2 warm-up pages. Okay. Hopefully you've been looking at some of those, stimulating your thought. Looking for some of that information in your textbook readings. Let's start on the second page with polarity of covalent bonds. Okay, hydrogen molecule, HH, is nonpolar. All right? There's no difference in electronegativity. And so the 2 electrons in that bond are sort of just equally shared between the 2 nuclei. And we call it a nonpolar bond, nonpolar molecule. On the other hand, with HCl, we have a difference in electronegativity, a pretty large difference. Chlorine more electronegative, being to the right of the periodic table. We can illustrate this with a dipole arrow, with a plus on this end and electrons being shown this way with the arrow. And so if we draw the 2 electrons in here, instead of equally dispersed, it's sort of more like that. Basically, you get my drift. I'm trying to say the more the electron cloud is towards the chlorine. Does that look like that at all? Okay. Chlorine is greedy. Pulls the electrons. All right. Of the chlorine. So I'm always doing this. All right. Those electrons. Did that hurt you, Elba? Right. That's that chlorine there. Illustrated with the dipole. Now because of that, the chlorine sort of takes on the electrons towards it. And we call it partial minus. The electrons are moved away, partial plus. It's still covalent though, it's still sharing. This idea of partial plus, partial minus, we just have to sort of envision. Okay? Just the electron cloud moving. It's a little bit sort of. Now what happened if the chlorine just took the 2 electrons and separated? The ionization, the chlorine would become completely minus, getting ions. So we're not that far yet. It's still covalent, but it's polar covalent is what it's called. And the molecule has a molecular dipole moment. That basically the molecule has some creation of charge. As I pull, I take on sort of minus, and that's the plus end over there. And we can see that with experimental evidence, the consequences of it. Basically, we're going to look for polar bonds. Now, carbonyl is a very common polar bond. Oxygen is more electronegative, and so we can draw the dipole towards oxygen. We can also show it like this. That oxygen's got a good amount of partial minus character, and the carbon has a good amount of partial plus character. So the carbon is somewhat electrophilic. And ultimately, when we start doing reactions, it boils down to pluses like minuses. So because we know the dipole is here, we know that carbon's a little partial plus. If we have a minus around, it'll be attracted to that carbon. And it's almost as simple as that when we start doing reactions. At least it's the first thought. We can have other polarities. Which is more electronegative, iodine or chlorine? Chlorine, higher in the periodic table, so the electrons are pulled that way. We can illustrate it with the dipole arrow. That's more negative than this. In organic 2, we show you a reaction with that. We're looking for which atom is partial plus? That's the iodine. Okay? Chlorine is pulling the electrons away from it. But it's not ionic, it's polar covalent. All right, water. You know, these we just got one bond, and so the molecule that's all there is. Let's skip this one. Here we got the CBR, bromine more electronegative, pulling, leaving carbon partial plus. That can be shown with the arrow, or you can put your dipole like that.
So either one is acceptable, you don't have to do both?
No, either one works.
Okay.
Ultimately, you got to know the consequences of this when you start using it.
Okay, but if you ask us to show a dipole limit, we could just put the partial charges on it or draw the arrow.
Either way works for me.
Okay.
Important here is we never consider any dipole difference or electronegativity difference between C and H. Look on the periodic table, there's a slight difference, but it's not enough to be consequence. So we never consider it. That's why when you have just hydrocarbon, well, CC, there's no dipole there. CH, we don't consider it at all. And so this is nothing but nonpolar bonds. It's nothing but a nonpolar compound. Now, if we stick a chlorine there in place of one of the H, now we have this polar end to it. And the carbon's partial plus, partial minus. Now we have this polarity here. Otherwise, we didn't have that. Here, I think we're going to move down. What's the dipole here? Which halogen is partial plus? Yeah, partial plus, partial minus. Chlorine more electronegative. Yeah, let's do water down here. Got a variety of compounds. Up there, we were looking at sort of individual bonds, and with ACl, there's only one bond to the whole molecule. So that just gives you the answer to the whole molecule. Down here, we're going to have multiple bonds to consider. And then we will assess, overall, is it polar? What we're going to look for is, do the individual dipoles cancel or not? If they cancel, then we can say it's nonpolar. What about water? Let's see. OH, there is a dipole, and so we go like this, leaving plus here. Electrons being pulled toward the oxygen. We also have electrons being pulled toward the oxygen that way. Are these equal and opposite? Do these cancel? No. Why not?
Both.
Ah, we got to consider the right geometry. I drew it sort of linear. It's really tetrahedral, right? We draw one H here, the other H is here. And then we got two lone pairs, one coming forward, one going back. So really the bond angle between the HOH is what? Approximately 109.5. Oxygen pulling. Question is, yeah, there's two individual polar bonds, but is the molecule as a whole polar? Do these cancel out? They do not cancel out. What we have here is, it's like summation of vectors. These two are coming this way, creating a net dipole sort of right through here. And this is the molecular dipole moment illustrated by the bigger arrow there. Water is a polar molecule because the individual dipoles do not cancel. In the next example or two, we'll see some that do cancel.
My question is, they're not the lone pairs, which cause the bond angle shorter?
Yeah, it does. Yeah. I'm not going to consider any variance more than that. CO2. Polar or non-polar molecule?
Non-polar.
Why do you say non-polar?
Cancel.
If you draw a Lewis structure, you're going to get this. Is it linear like that, or is the other oxygen sort of like this?
Linear.
How do you know it's linear? Two regions, SP. Okay, this carbon's SP. It's linear. You have dipole here, and you have dipole here. These are equal and opposite, and they're canceling out, making CO2 overall non-polar. Anybody question about the canceling out? We'll do some other examples, see if it clears up. What about SO2, polar or non-polar? Got to do a Lewis structure. How many valence electrons?
6.
Total?
18.
18. I'm going to put sulfur in the middle. Oxygen, oxygen. 2, 4, 6, 8, 10, 12, 14, 16. It's only 16, right? How many we got? 18. I'll put all paired here. There's 18. What kind of charge do we have in this structure? Minus, what is this?
Plus
2 plus. It's net neutral. SO2 is neutral. If it had a charge, I would have showed you a charge. Net neutral. Is this the best Lewis structure, or would you like to do something?
1, 3 bonds.
Sulfur doesn't have an octet. What do you want to do?
Add a bond.
Let's ask these electrons to move in here. What does that mean? We're going to have double bond to S. That's minus. This is plus. That's neutral. That's a resonance structure. It only varies in the way we place the electrons. If we just work with that structure at the top, what type of geometry do we expect with that sulfur? Now we could move this in again and expand that octet. Let's stick with just 2, 4, 6, 8 around the sulfur. So if we get to that point, what type of geometry around the sulfur? I see 3 regions, 1, 2, 3, trigonoplanar. So that means we have sort of lone pair region, oxygen here, and then oxygen here. And now we see trigonoplanar with 120 degrees. At this point, do we have dipole between sulfur and oxygen? Oxygen's more electronegative, so we have pooling. Oxygen's more electronegative, so we have pooling. Do these dipoles cancel each other out? No. Only way they would cancel each other out is if that was linear. But that's not linear because the sulfur has a lone pair, essentially. If a lone pair wasn't there, that would be linear, like CO2. It does not cancel each other out, so this is polar. And if we do a net dipole, it would sort of be straight down. It's kind of counterintuitive because we got a long pair right there. It's not going to go there, but hopefully everybody, it's definitely a polar molecule. So they do not cancel. CCl4, called carbon tetrachloride. Carbon with 4 chlorines. What's the geometry or hybridization of the carbon? chlorine, chlorine, one forward, one back. We've got 4 polar bonds, but what about the molecule as a whole?
Non-polar.
Here it's a little bit more difficult to see because we have 3 dimensions. Pretend there's chlorines on each end here. Straight up, straight in the board, one forward, one back. All chlorines are pulling. They actually do cancel. This chlorine's pulling straight up, but here you got 3 pulling down and to the side. Those 3 down and to the side sort of sum to 1 straight down. And that summation straight down cancels the one that's truly straight up. Okay? Y'all do some of this in physics or math where you do vector addition. Basically, a tetrahedral carbon with 4 identical things on it is going to be nonpolar. It's going to be canceling. So carbon tet's nonpolar. What if we replace one of the chlorines with an H?
Yes.
Now I know I'm able to erase and you may not be able to do it as quickly. We could change one of these to make it a bit more clear. Now that's CH. Okay. Chlorines are still pulling, and these 3 to the side sum up to 1 net dipole pull straight down. Is there one going straight up to cancel that? No, the CH doesn't give you a dipole to cancel. And so you really have a dipole sort of straight down the gut there. You drew that. See, it's kind of hard to work with 3D. These 3 sort of around give 1 just straight dipole straight down. In terms of electron movement straight down. By the way, CHCl3 is called chloroform. You could call it trichloromethane. Chloroform used as an anesthetic back in the 1800s. Question?
Well, what if you would change the Cl to an F instead of an H? Would it have been
Change all 3 chlorines to F?
No, just one. Instead of having 4 chlorines, you have 3 chlorines and like a fluorine.
And a fluorine? That gets tougher because you've got 3 chlorines pulling down. I guarantee it won't equal the F going up, but it will be closer to equal than with the H. Because at least you've got something going opposite. But it's probably not going to be exactly. It's probably still polar. But that gets into, it's not as easy to judge. I guarantee you 1F is probably not going to equal 3 chlorines going down like that. This is called dichloromethane. But if we make 2, so we can call the black still chlorine. Dipole, dipole. For a net dipole straight up, there's nothing coming down to cancel that. So there's going to be a dipole going up. It's going to be a polar molecule. Nonpolar, polar, polar. That was the last one. Now we move on to ionics, which is the extreme where that greedy chlorine or that greedy electronegative atom it no longer wanted to share it, it just took the electron. Okay? For example, if you had sodium chloride, first off, we know it's not covalent. We know that things to the far left on the periodic table, things to the far right are going to bond. We're going to be ionic, Basically, that chlorine just takes the 2 electrons and says, I'm not sharing anymore. And when it does that, we just move the electrons over, 4th lone pair minus, that becomes a plus, and it just becomes ionic instead of polar covalent. Typically, your metals like sodium, potassium, calcium are going to be ionic, or ion pairs. So that's the extreme. That's pretty straightforward and nothing really new there. Question?
Yeah, you said dipole methane is polar, but I know this is like actually like a largely contested thing on whether it's not polar or polar, but I feel like most sources say it is non-polar. Dipole methane.
Well, when we get to solvents, I will say something about that. I call dichloromethane nonpolar.
Okay.
But I'm basing that not on what we just did. I'm basing that on practice in lab.
Okay.
Okay? So you gotta be careful. Dichloromethane is a polar molecule.
Okay.
But I call it a nonpolar solvent. Why do I do that? Okay? When we get to solvents, I'll say a little bit more about that.
Okay.
Okay? All right. Now again, most of the stuff we presented, probably what you're going to need to do is do a little work on it, see what kind of questions for next time. All right? Office hours, SI, et cetera, problems in the workbook, problems in the warm-ups, and ultimately, come test day, you're ready to answer questions about polarity. Let's move on to physical properties, okay? For a building, okay? We'll see polarity here. 2 main things we'll talk about, boiling point, melting point, and then solubility. The boiling point, for molecules to boil, the molecules must overcome all intermolecular attraction, which hold the molecules together. Okay? Say this classroom is a beaker and all of you are individual molecules. Well, sitting in the beaker, you're all sort of probably like holding hands and arms and stuff, okay, stuck together. To get you to boil, I have to ask you all to just break your intermolecular attractions. Stop holding hands, stop, doing all this type of stuff. I have to put enough heat in there to get you to break those interactions. The more interactions you have, the more heat I got to put in, and thus the higher the boiling point is going to be. Okay? That's what I just said. In general, higher intermolecular attraction equals higher boiling point. Are 2 molecules really holding tight, hugging and everything, or are they just kind of holding like this? That's not going to take much heat. What type of intermolecular attractions are possible? Here are the 4 types. We'll go over each type. They're listed from weakest to strongest. Ultimately, they all deal with polarity. Because ultimately, all your interactions are because I have a positive end and you have a negative end and we attract to each other. But that can vary. The strength of those. First type is going to be van der Waals attraction. Also known maybe as London dispersion forces, London forces, that type of thing. I pretty much group it all together. I call it van der Waals attractions. By the way, these are different intermolecular attractions. You can also call these intermolecular forces. I don't know what term you used in Gen Chem. You may call it non-covalent interactions. Because we're not talking about you all being covalently bonded to each other. You're just interacting by these non-covalent interactions. Van der Waals. Let's start by looking at an example and then explain it. If you look at these 4 hydrocarbons, okay? By the way, this is propane. 3 carbons, alkane, propane. I mentioned the nomenclature video is now on YouTube. And I ask you to watch that on your own. Okay. So we got propane, and then here we got pentane. Boiling point of propane is negative 4.2, so at room temperature it's a gas. Already boiling at room temperature. We burn our grills with propane gas. Pentane is 36 degrees, and so at room temperature it's a liquid. Higher boiling point. Why is this one higher? Well, the first answer is it's got more IMFs. That's what makes boiling points higher. But we got to explain more than that there. How does it have more IMFs? What type of IMFs does it have? The only thing it has is van der Waals. Okay? That's the only type of IMFs it has. What are van der Waals? Van der Waals is sort of when the molecules bump into each other. What's on the outside of a molecule? Electrons. When the electrons bump into each other, they sort of undergo some fancy word called perturbation. They sort of get jostled around. And as these electrons approach those electrons, they kind of back up and stuff. All this sort of creates some fleeting, very weak pluses and minus regions. To me, it's a little hand waving, a little bit nebulous. You can read about it. It's very weak, though. Question?
So does that mean if you just were to have one molecule of an alkane, there would be no IMFs because there's no contact between another?
That's a good point. Sometimes I think people that do that talk about gas phase reactions because they want to get to just one molecule and eliminate IMFs. Possible, yeah. We're dealing with bulk samples, though, with lots of molecules. Okay, here's the sum. The more surface area the molecule has, the more it's going to have a chance to bump into another one and create these fleeting dipoles. Smaller propane, less surface area, not as much room, not as much bumping in. You don't get the plus and minus created as it bumps in. Pentane, more surface area, more fleeting dipoles, and thus more IMFs. Basically surface area contact. Increases the IMFs, increases the boiling point. That's why the boiling point's higher. Questions?
Is that why alkanes evaporate pretty fast?
Right, they don't have much holding them together. It's like you all are just held together with the pinky, okay? And all it takes is a good wind to come by and you're like, okay. Later on, we're going to be bear hugging and doing all this. Okay? Van der Waals is weakest interaction. Why would we go over here to this sort of very branched that's a 5 carbon, but it's branched. It's like a cross. Why does it actually decrease and go down to 10? I mean, these are both 5. What's the difference? Less surface area over there. I'll redraw it, but if I do surface area, that carbon is sort of in the middle and it doesn't sort of add to the surface area. All right, here's a take home. When you get branching like that, branching decreases surface area and thus decreases IMFs and thus decreases boiling point. You see, the middle guy doesn't contribute. If the other guy, extra guy was out here, I don't know how you do that without adding another carbon. Branching decreases surface area, decreases boiling point. And so that's why the one on the end went to actually decrease compared to the middle.
If branching decreases surface area, I'm assuming then the rings decrease it even further?
A ring?
Yeah.
Yep. I mean, probably. It depends on what size ring you're talking about. I don't have a good example here. You can extend any of this discussion to various things. Probably ring would have less than an open chain. important thing up there is to rationalize the 3 trend and why the last one actually goes back down, even though it's also 5 carbons. Okay. Let's move down here. Oh, I had it over here. Yeah, I had some. Let's look at number 2. Number 2 is going to be number 2 up there, dipole-dipole. This is going to be a bit of a stronger. Instead of a pinky holding together, we're going to now maybe hold hands. Stronger. Look at this trend. This alkane, 36 degrees, boiling point. If we throw a carbonyl there and now have a ketone, boiling point higher. Also higher if we had a chlorine there. Why is it higher than this? Well, do we have a dipole? Here we have a permanent dipole. None of that sort of bumping into each other dipole stuff. Permanent dipole. Here we have a permanent dipole. Do you have a permanent dipole here? No. All you got there is that weak bumping into each other, fleeting van der Waals stuff. Permanent dipole, now you've got a partial plus in. Let's say we're 2 of the same molecules. But you've got a partial plus in right there. I've got a partial negative in. We're going to be attracting to each other. And because those are permanent pluses and minuses, we're going to hold like real firm. Okay? Pluses like minuses. These aren't fleeting pluses and minuses. They're real, true. Same thing over here. We've got partial plus, partial minus. I'm probably showing you an illustration of that below. This is sort of illustrating that with the partial minus sort of attracting to the partial plus. I'm showing the non-covalent interaction as sort of a dashed attraction, not like a solid line as a bond. It sort of indicates a non-covalent interaction. So all those molecules start holding hands firmer. Now we can look on the next page. Let's compare these two. This alcohol, 118, the alkyl fluoride, only 78. Why is this one higher? Good. You're able to read right there. Number 3, hydrogen bonding. Does this have any dipole? Yes. Yeah, it does. What about this? Yes. Let's draw this out a little bit better. Can we do what?
Put it down.
Hydrogen's taking the electron.
Shouldn't it be the other?
Your arrows flip.
Shouldn't the oxygen take the electron?
The hydraulic alcohol.
And it has a friction
What's this one? Partial plus there? Sorry, I got distracted. Okay. Did I get the other one right? Chlorine? Yeah, I got that one right. These both look like permanent dipoles. There's a huge difference. This permanent dipole is much larger. Okay? Whenever you have an H and then an oxygen, nitrogen, or fluorine, that is a huge dipole. Much larger dipole. And this is going to lead to what we call hydrogen bonding, which is nothing more than a special name for a pretty extensive dipole-dipole interaction. Now, hydrogen bonding takes place again. Let's just get rid of that. We either have an O, N, or F. this will interact with the H that's on a O inner F. This is your very strong dipole. HF, because it's just a single molecule, it's sort of very uncommon, not seen that much. A lot of partial plus here. When you have an oxygen, nitrogen, or fluorine lone pair, these will heavily associate with that by your non-covalent interaction. Either way. Perhaps best to illustrate it here. If we have our alcohol, which is up there, what is it doing? The oxygen lone pair has an IMF with the H of another molecule. That looks like a dipole-dipole interaction. But because it's the H and the O, it is the H and O inner F, it's super strong, and we no longer call it dipole-dipole. Instead, we call it hydrogen bonding. Okay? This is illustrating a very strong hydrogen bonding network. This is like, instead of holding one hand, we now have two, and it's like wrapped with duct tape. Okay? Let's finish up here. In this scenario, the H is called the donor, but it's got to be on one of these atoms. So that's the donor, and then the lone pair is called the acceptor. Now, of course, the lone pair is partial minus. Those electrons are minus. That minus associates with the partial plus H. You get your non-covalent interaction. You got to have both of these to do hydrogen bonding, just like Velcro. For Velcro to stick, you have to have the fuzzy part and then the not so fuzzy part. Okay, you got to have both. We'll pick up here next time. Please look ahead. Whenever there's questions in the handout, please try to do the questions. And then we also have the acid-base handout, which we'll be moving on to on Thursday, acid-base chemistry.